In this video, I'm going to talk through the MEI Extra Pure 2022 paper from the further math syllabus. I'm going to go through each question bit by bit with the mark schemes up so we can talk through and see what we need to get down. Before I get into the questions, which I'm going to timestamp at the bottom, there's a little bit of general feedback that you should watch out for first. And that's mainly to do with the command words and the level of detail that you need to show and the level of rigor that you need to show. If you see a question that says explain, or more importantly, that says determine, you need to give working to be able to get all those marks there. You will not get full marks for simply a correct final answer without working backing that up. That comes up in a few different places, so we really need to watch out for that, and I'll flag it as we see it question by question. Okay, so question one, this one that we've got on the screen at the moment. We've got these three sequences, and they've got some of them are fairly complicated recurrence relationships here, and we couldn't realistically solve those easily. But we've been given the outputs from a spreadsheet here, and we're asked to describe the behavior, including what happens as n tends to infinity here. So that's what we need to go through, and we should see there's 7 marks here. So we're going to have to give a few different pieces of information to make sure we justify getting those 7 marks. Okay, so the first one we've got 8n here, and it's just going 3, -1, 3, -1, 3, -1, and so on. Terms that a few people said were saying it alternates between 3 and -1, or that is oscillates. Oscillate is a term from the spec, but oscillating is a more general term just to say something's going back and forth either side of a certain value. This is more special than just oscillating. When it's got a repeating sequence like this, then we say it's periodic. So you need to say periodic for 1 mark. And then the extra detail we can give here is the period it has, how often it repeats. It has a period of 2 because it repeats every 2 terms there. So that was where your second mark was coming from in describing the AN sequence. There's not a lot to say as n tends to infinity on the AN sequence because it's just going to continue repeating. You might want to say just make sure you've covered yourself, but you didn't need to in this case. Bn in different doesn't repeat, but here we do see there's a few different things going on. So it's bouncing either side of the value of 2. So in this case, it is oscillating, and that's the best term to use because it's not repeating, it's not periodic, but it's oscillating either side of this value of 2. So oscillating gets you 1 mark. The next thing we need to say is, well, what else is going on here? It's also getting closer and closer to 2. What name do we give to a sequence that gets closer and closer to some limit? We're going to say that it's convergent. That's our second mark. And the third mark is we should say what our limit is. So some people here wrote something like as n tends to infinity, bn tends to 2. I think that should be completely legitimate and fine. Another way of phrasing that, and the way it says in the mark scheme, is to say that the limit is 2 as n tends to infinity. So that's another way of stating that here. So this is what the mark scheme is looking like. We wanted you to say it's oscillating, convergent, and has a limit of 2. And the third one here for Cn. So Cn, it just keeps getting bigger and bigger and bigger and bigger. So it's definitely not convergent. So the opposite of convergence, say something's not convergent, is divergent. You could have here just said as n tends to infinity, Cn tends to infinity, but divergence is a good technical term to use here. And the second thing, which I've mentioned in passing there, is it's increasing because we can have things that are divergent and oscillating. We can have things that are divergent and decreasing and go to negative infinity. So we want to make clear it's strictly increasing. Each term's bigger than the last one. That's what we want to get at, and that's the final mark here. Just to show what's in the specification about this part of the scheme here, because all these terms here, limit, convergence, divergence, periodic, oscillating, they're all straight from the specification. So you want to make sure you're using that correct vocabulary when these questions come up, rather than just trying to put it in your own words. Be precise, use the language on the specification. Okay, let's go across and have a look at question 2. So question 2, matrices question from the ones I marked, it's pretty well done. So the first bit here, characteristic equation, I think everyone I saw knew that this means the determinant of a subtract lambda I is equal to 0. and then did some working towards showing that. So I've not even put a bit from the mark scheme in here because I was generally well done. The important thing is it's detailed reasoning. You need to make sure you don't jump from just having a huge expression in terms of lambdas to the thing you're given. You need to make sure you're showing some algebra, it's showing some intermediate working to show yourself getting there. So just make sure you've got sufficient intermediate steps. But that was pretty well answered. In 2B, using the Cayley-Hamilton theorem to determine A inverse. Now, it's important to use the word determine here because obviously you can just get A inverse from your calculator, but I wouldn't be using the Cayley-Hamilton theorem. So first thing here, what is the Cayley-Hamilton theorem? It's that when we replace lambda with our matrix that is satisfies its own characteristic equation here. Two things to watch out for. Firstly, our matrix is called A. A few people just putting M in because M is usually our matrix. Use the correct notation from the question here. The other thing to really watch out for is you don't just have plus 64 anymore. When it becomes matrices, it doesn't make any sense to add 64 to your matrix. We're adding 64 loss of the identity matrix. Strictly on that right-hand side, you should have zero underlined because it's the zero matrix now. It's not just the number zero at that stage. Then we want to multiply everything by A inverse. The mark scheme explicitly says, or the examiner's report maybe explicitly said, they did penalize you if you said you were dividing by A. We can't divide by a matrix. We can multiply by the inverse, which is the analogy in this case. So that's what we're doing here. We're multiplying through our by A inverse, and then we can rearrange to get A inverse in terms of A squared. At this point, because it's determined, you can't just whack this all into your calculator straight up with no working. You need to make clear that you're subbing in your A and write down an expression. Either writing down your matrix squared, or what I did when I worked through this question, because I didn't even know if the mark scheme would allow that, is actually doing that matrix squared. Now, obviously, I'm not doing that pen and paper. I'm getting my calculator to do that for me, but I'm making sure I've written down what I get when I square it. And then we need to combine getting an answer. We shouldn't be getting a wrong answer here because even if you have made a mistake in your numbers, you can go onto your calculator, you can enter your matrix, and then you can find the inverse matrix on your calculator. The inverse matrix on your calculator won't look very nice. It won't have this 1 over 64 factorized out. So multiply your answer by 64 and check it gives you the matrix that you're expecting from your working rather than having to deal with fractions inside your matrix. Part C, again, is a determined question. And that's really important here because actually, I think part C is relatively easy. We know to get a diagonal matrix, we're trying to find the eigenvalues, and we've already got a characteristic equation. It's this cubic. So we just need, once we get the values of lambda, we're largely done. So you need to make sure here you're showing how you're factorizing that cubic. Use your factor theorem, get a factor, factorize it out, get a quadratic and factorize that. Don't just say lambda equals 2, lambda equals 4, lambda equals 8. If you did that and wrote down your correct diagonal matrix, you got 2 out of 4. But because there's that determined there, you need to make sure you're showing working and you can't overly rely on your calculator on that question. Okay, going across to question 3 now. 3A, the algebra is bad, but it's a straight up nice recurrent relations question. You should be backing yourself and taking the 6 marks here. So first step, do get your complementary function. If you're unsure about this complementary function because it's a first order, you treat it just as a second order and you just do 5 lambda subtract 4 equals 0. You just don't have any lambda squared because it's not a second order equation. So then you're going to get lambda equals 4/5, and then your complementary function in this mark scheme down here is just a constant times 4/5 to the n. So Tn equals 4, a constant times 4/5 to the n solves your 5Tn plus 1 subtract 4Tn equals 0. We now need to worry about the right-hand side. We now need to worry about our child function. We have a quadratic, so we're going to guess the most general quadratic, an squared plus bn plus c, and sub this whole algebraic mess into here to work out what a, b, and c have to be. Simply expanding your left-hand side and then comparing your coefficients. There is a fair amount of algebra to do here. They're making you earn those 6 marks. But get your value of A is 3, your B is -2, and your C is 1 by comparing your coefficients of n squared of n and yours is constant, and those should come out. Your general solution is then your complementary function plus your particular solution. And that gets us this expression here, which they've labeled gen sol. But we're not quite done yet because actually we're given one more piece of information in the question. We are told in the question here that t0 equals 7. So you need to sub in n equals 0, t0 equals 7 to get an expression and be able to solve for this constant. And then you get your solution that satisfies your initial condition here. Okay, part B. It says here that we want to determine the limit. Because of that, if you just write the correct answer, you're not getting a mark, even if you might be able to just look and say. So the best thing you're best to do here is write out what your Vn is here. So in the first one, we're doing Tn, well, we've just got over n cubed. So if we do this expression divided by n cubed, we end up with these four terms. Each of these four terms tends to 0 as n tends to infinity. So our limit of the whole thing as n tends to infinity is 0. So you're best to explicitly say here the limit is 0 rather than just say Vn tends to 0 as n tends to infinity. I would explicitly make sure you use the word limit. This notation is clearly acceptable as it's used in the mark scheme there. Repeat that on part 2. So on part 2, we're just going to do the same, but we can do over n squared. Well, what changes now? When you do over n squared, this term just becomes a 3. So this bit still turns to 0, this bit still turns to 0, this bit does, but this term here is stuck as 3, so your limit is 3. And finally, when you're just dividing by n, you end up with a 3n term. Now, as n tends to infinity, 3n tends to infinity, so the limit doesn't exist, and that's why we're being asked whether the limit exists. So, and it says then, or show the sequence is divergent. So I would say the limit does not exist, and the sequence is divergent. You didn't need to say both, but you're covering yourself by doing that. But main thing with the determine, just saying 0, saying 3, and saying divergent isn't enough for the mark. You need to show the algebra of how you decided that. Going across to question 4. So 4 and 5 were the harder two questions. So question 4a is a particularly strange one for groups, I think, setting this up. So we're given some information. We're given the rough form of our operation here, being K1a subtract K2b plus K3. And we're told two things. We're told that O composed with O is 2. That's a natural place to start. And if you sorry, I don't know why I call it O, 0 composed with 0 is 2. So if you replace A and B with 0, you just end up with K3 equals 2. That's the first mark. That one's quite nice to get. There's not much else we're told apart from this third bullet point here. There's an identity element that exists in A. Now, obviously, if it's a group, we know that needs to be the case, but they're telling us that because we don't know it's a group yet. So what does this tell us? What does it mean to have an identity element? It means that E composed with A is equal to A, and that A composed with E is equal to A, that both those things are true. So using the second one, subbing that in, we get this equation here that's in the mark scheme. Now, because this is true for any value of A, we can attack this like we would an identity. The coefficients of A on both sides of this equation have to be the same. So we just have to have K1A equals A or K1 is equal to 1. And then similarly, we're going to use that E composed with A is equal to A. It notes that this is going to give us a different piece of information, which is really useful. So when we do that, we get this second equation, which again is true for all values of A. So compare our coefficients of A this time, and we get negative K2 is equal to 1, or K2 is equal to negative 1. And so we get exactly what we were asked to show. So scrolling down here, trying to find the identity, the mark scheme here just says it because it does say state. It should be nice for us. Well, the identity, we know now that we want A composed with E is equal to A. So if we do that using A plus B subtract 2 is equal to A, then we're just going to end up with B subtract 2 equals 0. Sorry, B plus 2 equals 0, so B is equal to negative 2. I should really have used E rather than B there. Sorry about that. I just changed halfway through there. So that's E. That's E. That's E, and we get our identity to be -2. You don't need to show any work in here because it's a state, but that's where it's coming from. But that was generally well answered. Part C, you need to make sure you keep some rigor here. This is an explain question. Yes, it's only 1 mark, but you need to be very clear that you're looking whether B composed with A is equal to A composed with B, and you need to show a bit of algebra to back that up. The examiner's report explicitly says it's not okay just to say addition's commutative, therefore the operation's commutative. You need to show some algebra to back that up. So when in doubt, be rigorous, show the algebra to back up any of your claims. We're then into determining whether or not this is a group. From the ones I marked, there's very good knowledge of all the axioms, but again, it's just lacking that rigor sometimes about how to put your point across. So, first thing to consider, the first thing the math scheme deals with is closure. We're going to take two elements in our group, and you could either use R or A here, either was completely acceptable. Note, R means the real numbers, not the rational numbers. So you can take either notation was fine because they were equal here. And then you need to explicitly state, so A or B, which is A plus B plus 2, belongs to the real numbers. It wasn't sufficient just to say addition is closed in the real numbers. You needed to state clearly what you were doing there. Next thing to check is associativity. Now, as a reminder for associativity, it's checking that these two things are equal here. Now, little bit of algebra should give you that they're both equal to A plus B plus C plus 4, and therefore you should state, so it's associative. Make sure you're setting it up, testing, and then concluding after you found it. Don't just do something where it says associative colon and then do the work. Like at the end, make sure you state these things are equal, so our operation is associative. We know that we have an identity and we know that our identity is in the group. It's just worth making sure you state that obviously we have an identity -2, which is in the real numbers. Here they only make that statement in the conclusion. Uh, well, actually, yeah, they just made this statement in the conclusion here, but I'd make sure you cover it. I'd always cover it before the inverse because the inverse doesn't really make sense without the identity. And then our inverse, we need to, so for an inverse to exist, we need A composed with, and you can call this B or you can call it A inverse. I'd probably call it A inverse. We're trying to find A inverse so that we get our identity. So note what we're saying we need. We need A plus A inverse plus 2 to equal -2. So if we rearrange this, we're going to get A inverse is equal to -4. Sorry, I just lost my pen a second. -4 subtract A. So it has an inverse. We need to check one more thing. We need to state that it's in the group. Now, obviously, if A is in the real numbers, -4 subtract A is also in the real numbers. But make sure you state it. Make sure that it's in the group. You needed to get that mark there. And then once you've checked your four axioms, state, yes, all the four axioms are satisfied. So this is group. Get that conclusion mark. To show that, so you should have that conclusion mark there. Okay, final bit of question for here, and I'll be honest, I'm not a big fan of it, is explaining whether our answer would change in any of these cases. And in part one and part two, our answer doesn't change, but just saying the answer doesn't change when it's an explain question isn't sufficient, even though you didn't need to say much. So when we're looking at the integers, well, let's just go through in our heads quickly. The integers are still closed. If we do A plus B plus 2, we're still going to get an integer. There's still an identity, which is an integer. Each inverse is still going to be an integer, and they're still associative. So it was sufficient here to say just the argument still applied, but you should make it clear here that yes, you're considering all those arguments. There were some answers which carefully considered the main bits, but didn't state anywhere that and the other things still apply as well. So it needed to be obvious each of those still applied. If I had time in this, I'd probably go overkill and just do quicker, but mentioning each axiom again rather than risking it. but you didn't need to for 1 mark. You just needed to say each argument applied. The same happens again in part two because with the even numbers, we still have closure. Our identity is an even number. Our inverses are still going to be even numbers. Part three is the one where it changes and we don't have a group. Because when we're looking at integers greater than or equal to -2, then it's not quite correct to say an element doesn't have an inverse because as they give here, so the inverse of 2 is -6. What is the case is that our inverse isn't in the group. You did get a mark if you said, like, just it didn't have an inverse, but it was risky because it wasn't strictly true. Really, what you should be saying there is that uh, some of the elements inverses don't belong in the group, and even better if you can give a concrete example there, because one concrete example's enough to show something is not a group. Okay, on to the final question, the multivariable calculus question. So the first bit, partial differentiation. Uh, you didn't need to give it simplified, but I would very much recommend simplifying a little bit. The main thing to watch out for is just making sure you're careful with the negative outside the brackets. Sometimes that negative was slipping in the brackets, but the differentiation in part one was generally pretty well done and sensible simplification, more sensible than the mark scheme does here. I wouldn't recommend leaving it with a y here and a y here rather than making those y squared. That's risky because you can sometimes be penalized for not simplifying. You just weren't here. On part two, we're asked to find df by dy. So there's a reason they're turning this into a show that to save you a little bit because you need product rule here. But because to show that, you'd better make clear that you're doing some product rules. You'd better have these two terms clearly in the first place, and then a little bit of working to sort them out there. Part three is when this question really starts ramping up a little bit and gets a bit more complicated. If we're looking for the coordinates of stationary points, we're looking when df by dx equals 0 and df by dy equals 0. Let's know one of these is definitely nastier than the other. This df by dy, looking at this equals 0 is going to be a bit horrible. So let's start by looking at df by dx equals 0. So when df by dx equals 0, obviously, but state it, this e to the negative x squared plus 2x plus 2 times y can't equal 0 because that's always positive. So we're going to have the y squared multiplied by, so I'm just trying to work out how to write this. We're going to have the y squared times by the 2x plus 2 is equal to 0, which is going to give us either y equals 0 or x equals -1. Note you don't need both those things to be true for this to equal 0. You need one or the other. So these are two separate cases to consider. So now we need to go to thinking about df by dy equaling 0 and seeing which of those is actually possible. So when we sub in y equals 0 here, this is 0, this is 0, this is 0. So we just end up with 1 times e to the 0, which is 1. So when y equals 0, df by dy is 1. It doesn't have any solutions, and therefore there's not a stationary point when y equals 0. You need to consider it. You can't just ignore it without mentioning it. So that's one consideration. We're now instead going to consider x equals -1. Sub x equals -1 into this slight mess, and it doesn't become too bad. We get this equation here, this 1 subtract y, e to negative y equals 0, which only works if y equals 1. So our stationary point is when x equals -1, y equals 1, and then we're going to sub it and get our z coordinates. We need all three coordinates for our stationary points there. Okay, we now get on to looking at some sections here. So we're given the graph of z equals e to negative x squared, and we're asked to transform it to the section fx1. So this is replacing, I'm just going to go back up here and grab this. So we're replacing y with 1 in here. That's exactly, sorry, that's come out way too big. I won't try that one. Uh, There we go. We're back where we were. Okay, so we're just replacing y equals 1 into this thing here. And when we do that, well, what are we getting? We're ending up with z equals, so I'm going to have to scroll up and down for a second here after that failed. Just going to get z equals e to the negative and then brackets x squared plus 2x plus 2. So this, I don't think is obvious. This is a single maths question now, to be honest. What guess here to here, but it's a hard single maths question. So we definitely can't just do it by eye. We want to complete the square here and then see if we can compare it to this. So by completing the square for what's inside here, I'm going to get x plus 1 all squared plus 1. So this is e to the negative 1 multiplied by e to the negative x plus 1 squared. So what transformations are happening? This is kind of e to the negative 1 times by our f of x plus 1. So there's a translation by the vector negative 1, 0. Make sure you use the word translation and not shift or move or any less precise word. And then there's a stretch. Now, you can describe this as a vertical stretch. You can describe this as a stretch here parallel to the z-axis, because if you look at the graph, the vertical axis was the z-axis, not the y. Good news, you didn't get penalized if you said in the y direction here. You really should be saying in the z direction or in the parallel to the z-axis in this question, because that's the axis our graph was on here. In terms of sketching it, well, once we know what we're doing to this graph, we're translating it left by 1, and then we're stretching it. You just needed to make sure you labeled this maximum point as negative 1, e to the negative 1, which is where it's going to end up there. The next bit wasn't that well done, and there's actually a fairly common question for classifying stationary points here, even though it doesn't really give us much guidance in doing so. I've just written over it, so let me just get rid of this. So, looking at the final part here, we've got a stationary point. We know from our part A, our stationary point is a negative 1, 1. So our stationary point is at this point here, negative 1, 1. And at that point, we know the z's equal to e to the negative 1. We then know all these points on this contour, we're told is when z equals 0.25. Now, important question, which is bigger, e to the negative 1 or 0.25? It's fine to use your calculator to check that. E to the negative 1 is bigger. So because this is a closed contour, we're going down in all directions from our stationary point to our contour, and therefore we have a local maximum there. I would make sure you're saying the contour is closed, z equals e to the negative 1 is inside and above the contour. Therefore, we are going down in all directions, and therefore it's a local maximum. Tick all those things off. In this case, the mark scheme only required that we were going down in all directions to the closed contour. But I would make sure you say the point is inside and above the contour. Therefore, we're going down in all directions. There have been 3 markers in the past which have required more working there, more description there. Okay, almost there. On part E here, we're told we're given a point where z equals 0 and we're trying to find in vector form. So we know we want to get grad of f, which is our df by dx, df by dy, and negative 1. And, well, we've got our df by dx, we've got our df by dy, and we've got our negative 1. I would start by writing that down, even if you don't know what you're doing next. But let's go back and look at what we've got. If we're looking at when y equals 0, summing y equals 0 here, we get z equals 0 straight away. So that's useful. We're not told what x is. It turns out it doesn't matter, because once we know y is equal to 0 in fact, once we know if z equals 0, y equals 0, sorry, I went the wrong way there. So if z equals 0, then this thing must equal 0, because we know that e to the stuff is always positive. So we get y equals 0, and then subbing that into here, our grad of f just becomes this lovely 0, 1, negative 1. So remember that grad of f is the normal to your tangent plane. So if you wanted to write your plane in Cartesian form, you'd be saying that you're getting 0x plus y subtract z is equal to a constant. But subbing in y equals 0, z equals 0, you're just getting y subtract z equals 0. But you're asked for it in vector form. In vector form, it's wanting you to write it as your normal dotted with x, y, z, or dotted with r is equal to 0 here. So that's what you want to be, how you want to be stating this. final bit, I think, is a weird question here, but it's the final mark of the paper, so I think we can forgive them. So we're told the tangent plane intersects our surface in a straight line, and we're asked to write down in vector form what the equation of that straight line is. But what we should notice here is that we're looking at z equals zero on our surface, and z equals zero on our surface, x could have been anything. Y had to be zero, but x could be anything. So we could go in any direction in the x direction. We just needed y to equal zero. And we can also notice here that 100 is definitely perpendicular to our tangent plane, to our normal, so it lies in the plane. So the equation of that, so any multiple of 100 lies in both the plane and on the surface. I think that's a hard thing to spot there as the final thing. If you wanted to go more algebraic there, you could have gone right back to the start and just said, well, if z equals zero and y equals zero, x can be literally anything up here. That's what we're finding out. But like I say, weird one to finish off with based on one marker. So I think that's have a shot, but I wouldn't worry too much if that one's difficult to visualize there. Okay, thank you very much.